This is a review for Precalc Unit 2. The first three graphs are the absolute value graph, looks like a V, the quadratic graph looks like a U, and the cubic graph, which has the symmetry through the origin. The next three, the identity graph, which is a linear graph, the reciprocal graph, the constant graph. Notice it's a horizontal line. The last three are the square root function, the greatest integer function, or the step function. I don't have a calculator in front of me, but I believe the steps are y equals math right arrow 5 to pull up this int. And finally, this last one is not a function. Remember, vertical lines fail the vertical line test. One way to graph a piecewise function on a calculator is to press the buttons in this order, y equals math up up. You choose how many pieces there are. And when you go to put in the inequalities, if you press second math, there's a whole bunch of options for you. I'll start with this middle piece. It ends at -2 and 0, and there's a flat horizontal line between them. For this top graph, if you were to plug in a -2, that would give you 2. So I'm going to put an open circle there. And this is pretty much the left side of a quadratic. That's a rough sketch, but it'll look something like that. For the bottom graph, let's do this in green. I'm going to start by plugging in 0. That's going to give me a -5. I'll put an open circle down there, and I know that my slope is 8. So I'll put the first dot over 1 up 8 and draw a line like that. And there's what my graph would look like. When it comes to 1.7, think of these transformations in groups. The first one, we are moving up, down, left, and right. The up and down go over here, and the left and right are there with the x, and they're opposite. When we put things in function notation, the parent function part goes away. We don't see absolute value or cubed, but the transformations are still there. And we reference f for the parent function. For the next group, these are the reflections. Depending on which axis you are reflecting over. The x-axis, your negative goes out here in the front, and the y-axis, your negative goes here with the x. Here in function notation, the negative goes here or there, depending. In the last category, the stretching and shrinking, or sometimes I call it the scaling, the vertical stretch and vertical shrink go in front here, and you'll notice that stretch directly multiplies by 2, and shrink directly multiplies by 1/2. The difference for horizontal is that we are inside the parentheses next to the x, and a horizontal stretch by a factor of 3 goes in as 1/3, and a horizontal shrink by a factor of 1/3 goes in as 3. The function notation side follows a similar pattern. The 2 and the 1/2 for vertical are in front, the 1/3 and the 3 inside the parentheses next to the x for horizontal. So for this next section, it's about where the numbers show up, also what's happening to the graph. Notice that these are pulled up vertically, they're vertically stretched. We also see the 3 in front of the absolute value of x. Here, it's like the vertical are pulled down, and the fraction is in front of the x squared. This one, it's like the horizontal is pulled in, and notice the 3 is inside the bracket with the x. With the next 3, we keep that in mind, that shrink means shrink horizontally, stretch means stretch horizontally, and shrink means shrink vertically. So it's like we're pulling this down. Also pay close attention to where the numbers are, inside or outside the brackets with the x or in front. To tie together the concept, every time you have a vertical shrink, what also happens? A horizontal stretch. And what happens every time you have a vertical stretch? What also happens? A horizontal shrink. Sometimes they're the exact same, like in the case of these graphs, but when you have an exponent, often they're not exactly the same, they're just going in the same direction. For this first graph, if we consider the parent function looks like a u, that's f of x is equal to x squared, and we notice that we are moving this left 2, and it's reflected over the x-axis, this will give us our new graph. So you can use the rules from that table above, or you can try to guess and check on your calculator. Of course, the rules make it go a little faster, and sometimes there's more than one right answer. For this next one, we should have the identity function, which would look kind of like this. You can notice it's reflected over the y. And then depending on how you want to describe it, you could think of the translation as going left or down. It depends on the order and when you reflect. So either g of x or h of x would match this graph, and both would work. So for this graph, you have to pay attention to where the actual coordinates are, and what you would expect for the parent function, x squared. So looking at this graph, my first point that is actually even on an exact point here, not like between, is 2, 1. I also see here 4, 4. I'm looking at relative to where it would be at the start. If you think about how you would plug these in to the original parent function down here, 2 squared would not give you 1, it would give you 4. And 4 squared would not give you 4, it would give you 16. So look at the factor. What can we possibly be multiplying by to change that 4 to a 1 and 16 to a 4? If you also consider that we're moving up 2, you can do it one of two ways. You can put 1/4 in front like this, or you can put 1/2 attached to the x, because once it squares, you also get 1/4. Both of those answers will match this graph. So if I think about this one, I know that my parent function here is f of x is equal to x cubed. And starting from here, I go right 1, up 3 to land on this spot. That's not what I would expect. I would expect that if I plug in a 1 cubed is normally 1. So what sort of scale are we looking at to go from 1 to 3? So this will work, taking my equation and giving it a vertical stretch of 3 and including the translation down 2. If I wanted to find the alternate function that also worked, I'd have to put the cube root of 3 here, because once I cube that, that would give me a factor of 3 as well. When I add these two functions, it looks like this. I'm just combining like terms. There's only one x squared, there's only one x term, and then plus 3 minus 1 combines. Subtracting is very similar. The only additional step is to distribute the negative. So this is like minus 2x plus 1. So if I combine things, this is my result. For multiplication, I like using the box method. I set up my two binomials on the outside. This is 2x cubed, 6x, negative x squared, and negative 3. Put it all together. This is my result. For division, the beginning is simple. You just put them on top and on bottom. You also have to remember that this whole thing can't be 0. The bottom of a fraction can't be 0. So if I say 2x minus 1 is equal to 0, that's 2x is equal to 1, that's x is equal to 1/2, and that's the domain. X cannot be 1/2. Also watch out for the potential domain restrictions of a square root, because that cannot be negative. For a composite function, it's almost like nested functions, and we do the inside first, so I can replace this g of x with what it's equal to. And then I'm going to plug this whole thing into the x for the function f. After you plug in the root 3 minus x, the root and the squared cancel out. It simplifies to this, and there's your answer. For g of f, here's the first part. And I guess I should point out that should have been f of x there. That's cool. So here for this one, once I plug in x squared minus 4 in for x, I have this. It's like I'm distributing the negative here. And I get negative x squared plus 7. For inverse functions, we think of this as y is equal to 3x plus 8, and we switch them. So we have x is equal to 3y plus 8. We solve for y. So x minus 8 is 3y, and this whole thing divided by 3 is what y is. So if I take the function of the inverse, that means I'm looking at 3 over x minus 8 over 3, or 3 times x minus 8 over 3, plus 8. I took this and I plugged it in for the original x. Here you can see that the 3's cancel out, and then it's x minus 8 plus 8, which is just x, and that's what I want. I can also go in the other direction, start with the inverse, and work backwards. So here I take 3x plus 8 and plug it in the other direction for x. On the top here, I have plus 8 and minus 8, so it simplifies to 3x over 3, which is just x. Everything works for the first one. Think of it like this. Switch them. And when I solve for y, I have 5x plus 4. So let's plug in 5x plus 4 for x. And let's also go in the other direction and plug in x minus 4 over 5 for x in the other equation. On the top here, plus 4 minus 4 goes away, and I have 5x over 5, which is just x. 5 over 5 goes away, and I have x minus 4 plus 4, which is just x. Everything checks out here. For this section, all you had to do is the horizontal line test. You can see that this one is a no, and then these two are a yes. You could do it other ways, but the horizontal line test works really well. This is the absolute value function, and it's moved to the right 2. So I would be looking at a graph that looks kind of like this. And they say restrict the domain to only where it's increasing. So basically I have to figure out how to get rid of all of this. So what point am I looking at here? Well, that is when x is equal to 2. So let's say that for the domain, x is greater than or equal to 2. That's the first part. And now I need to figure out the inverse over that interval. So at this point, now my function is just x minus 2. Like the absolute value part is gone. So if I think about it like that, and I switch them, x plus 2 is equal to y. That's my inverse over that interval.